we want to use techniques from topology and geometry to study number fields. One way to do that is by putting a metric on the number field. Once we have a notion of distance on the number field, we can then start talking about open balls in the number fields. These open balls would then give a fundamental system of neighborhoods and thus giving us a topology on the number field. A natural way to get a metric is via absolute values. An absolute value on a field K is a multiplicative real-valued map on K that is positive on every non-zero element of K and vanishes at 0. And then, finally, we require that either for all elements x, y, and k, this absolute value satisfies the triangle inequality, in which case we'll call it Archimedean, or for all elements x, y, and k, the absolute value satisfies the following Huygens triangle inequality, in which case we'll call it a non-Archimedean absolute value. Now, given an absolute value, one can define an induced metric by taking the distance between 2 points x and y to just be the absolute value of x minus y. So, what would be an example of an absolute value on a number field? Well, for a number field k with a discrete valuation v, there is a very natural induced absolute value. We can define the absolute value of every element a, for example, to be, say, 1/2 to the valuation of a. But really, in place of 1/2, we could just use any constant c between 0 and 1. As an example, let's see what this comes down to in the case of p-adic valuation. Let us take p to be, say, 3, because why not? Then we have the following values for the valuation, right, at 1/9, 1/3, 1, 3, 9. So the corresponding absolute values are gonna be c to the minus 2, c to the minus 1, c to the 0, c to the 1, and c to the 2. Now, if we let c be, for example, 1/2, then the absolute values are gonna be given as follow. So you observe that the bigger the valuation, the smaller the absolute value. This means that for 2 points x and y to be close, x minus y must be divisible by high powers of 3. Thus, we have the following picture of the three-adic number. Let us figure out the three-adic distance amongst these points. Observe that the difference amongst these points here are 1899, which are divisible by 3 squared, but no higher power of 3. Thus, all of their p-adic distances must be c squared. Next up, let us look at the points in the medium disk that do not lie together in a small disk. Observe that their differences are 3, 6, 12, 24, i.e. their differences are divisible by just 1 power of 3, and no higher power. That means that their three-adic distances are all just equal to c to the 1, i.e. c. Now similarly, if we look at the points that all lie in this biggest disk but do not lie together in any medium disk, then their differences are not at all divisible by 3. So their distances are just c to the 0, i.e. it's 1. Now, observe that there is a very curious geometric phenomenon here. Let us consider this disk as a disk center at 7 with radius c squared. Then, just by definition, we know that every element in this closed disk is gonna have distance less than or equal to c squared from 7. Now, the true curious thing is that actually the distance between any 2 points in this disk, any 2 points, not just between a point and the center, the distance between any 2 points in this disk is gonna be less than c squared. So let's see why that is. So let's say x and y are 2 points inside this disk. That means that the three-adic distance from x to 7 is less than or equal to c squared, and so is the p-adic distance from y to 7. In terms of valuation, this means that the three-adic valuation of x minus 7 and y minus 7 is gonna be greater than or equal to 2. Now, by definition of three-adic valuation, this just means that x minus 7 and y minus 7 are divisible by 3 squared. This means that x minus y must also be divisible by 3 squared, or even more power of 3. This means that the three-adic valuation of x minus 3 must be greater than or equal to 2, and so its three-adic absolute value must be less than or equal to c squared. So you see, the geometry in the p-adic is very different from our usual geometry. In the p-adic world, any 2 points inside a disk of radius r must have distance less than r. Now that's an example of the geometry that we get by using a metric which is induced by a discrete valuation. Of course, our next natural question is, do all absolute values come from valuations? Or more generally, what are all the possible absolute values on a number field? We will answer that in the next episode.